Hi, this is Mr. Manley. In this video, I am going to look at solving some special log equations. First off, I've got this natural log equation. The natural log isn't what makes it special. What makes it special is when I apply the product property. So the product property of logarithms, I'm going to combine these using the property which says that ln of A plus ln of B is equal to ln A times B. So using that property here, I get ln of 5x plus 20. See that? Multiplying 5 times x plus 4, I get 5x plus 20. Now this is the special part. Now I'm going to use the one-to-one property to set x equal to 5x plus 20. So what happened here? What happened here is that I had a log of something and I had a log of something else. So since these logs match here, in order for the equation to be equal, these pieces must also match. Therefore, I can drop the logarithm and simply solve for x equals 5x plus 20. I did not divide by natural log. So please, please, please don't think that you're saying something like this. I'm not dividing by ln and dividing by ln and getting x equals y. I cannot divide by ln because it is an operation and I cannot divide by an operation. But I can use the one-to-one property, and although it achieves the same effect, I would not want you to think about it like that because that could lead to other errors in other situations. So this is the one-to-one property, and then solving from here, I get negative 4x is equal to 20, and x is equal to 20 over negative 4, which is negative 5. So it looks like my answer is negative 5, but on these problems in particular, and really any equation that you're solving, but in these equations in particular, we want to check that our solution is in the domain. And if I look back up here, and if I were to substitute a negative 5, then I would be doing ln of negative 5. Well, I can't do the log of a negative number. It's not in the domain. So since negative 5 is not in the domain, I'm going to eliminate this solution and say that the answer to this is actually no solution. And that's it. Okay, let's take a look at another special one. Here's one where we've got a variable exponent, and if you have received instruction from me, at least in logarithms, you know that I have emphasized that the purpose of a logarithm, the log operation, is to solve for a variable exponent. So that may be the conclusion that you jump to here, is that, well, I should use a logarithm to solve for this variable exponent, like so. And that actually would work. But I want to take a different approach here, that before I solve for a variable exponent, I'm going to stop and look and see if I can get a common base. And by a common base, I mean I can write both of these in the same base to a power. So what that means here is that I can write 16 as 2 to the 4th. And I can write 64 as 2 to the 6th. Then applying the property of logarithms, power to a power, what do? Multiply. So that would give me negative 4x minus 16 equal to 2 to the 6th. And what am I going to do here? The same thing as I did on the previous page. I've got this idea of I've got 2 and then there's something up here. So since these are matching, the 2's are matching, that means the exponents must match. So this is another application of the one-to-one property. Negative 4x minus 16 equal to 6. This is from this step to this step is using the one-to-one property. And then from there, we could solve for x. Shouldn't have a problem of a domain issue here. The domain of this is all real numbers. So I'm not going to solve that and figure out what x is. That's a simple algebraic equation to solve, and I would think anybody could do that. So let's move on to the next one. All right, so here I might take and glance at this and consider the bases and see that I can't write these as a common base. So I back off from that and I look at the variable exponents and think logarithms, because logarithms go with variable exponents, particularly when we are trying to solve for variable exponents. So I am going to use the definition of a logarithm here, like so. All right, and what I'm saying here is that if a to the b equals c, then log base a of c is equal to b. That is the definition of a logarithm. And you can match these up one for one and go, this is my a, this is my b, this is my c, all of that, 8 to the negative 8x is c, and then move those into the proper position a, c, and b down here. Or in this case, down here. So you've got to be able to apply that definition of a logarithm. You just stop and study. How do I get from this step to this step? And then apply that definition from here to here. Now that I've applied the definition of a logarithm, I'm going to apply a log property. And I lost my x here. I'm going to apply the log property, which is the power property, which says I can bring the exponent down like so. And then from here, we want to solve for x. What is it that we are doing when we are solving for x? We're trying to isolate x. We're trying to combine x's. Sometimes when we're dealing with polynomials, we are setting the equation equal to 0 and trying to factor, but we're not dealing with a polynomial here. So what am I going to do? I'm going to try and get these x's together. And what that means is moving this x over to the right. Now I've got the x's on the same side of the equation, right? And from here, I'm going to factor. So factoring out an x is going to allow me to isolate x. All right, and from here, I'm simply going to divide. So that'll be 2 over negative 8 log base 9 of 8 plus 1. And we could say that is a solution. That's a solution to the problem. I have solved for x. But we could have a couple of other ways of saying the solution depending on the instructions. One instruction that I've seen is express the solution to x in terms of log base 10 or in terms of log base e. So let's look at that. If I did it in log base 10, I could write it like this. And there, I simply use the change of base formula to convert from here to here. Log base 9 of 8 is equal to log 8 over log 9 by the change of base formula. And now these are in base 10, right? If I wanted to do it as base e, I could write it like this. There. If I don't like how this looks, and I actually don't, I don't think this looks very nice, I could simplify the complex fraction by multiplying through by ln 9, and I'd get 2 ln 9 over negative 8 ln 8 plus ln 9, simply by distributing the ln 9 in the denominator and multiplying it by the numerator. That looks a little bit more simplified, a little bit more compact to me. So that's one instruction that we could get, is to solve for x and write it as base 10 or base e. And then another instruction we could get is to solve for x and estimate to the nearest thousandth. And if that's the case, then this is just a big calculator entry. And we enter that into the calculator and then round off to the nearest thousandth. So those are just 3 looks at some different equations that we use logarithms to solve, or where we could use logarithms, as in this one, but we choose not to. And that should be adding to your toolkit about how to solve some equations. And ultimately, just know that what it comes down to is applying the properties of logarithms and the definition of a logarithm, and that expands the number of equations that you can solve, particularly equations where there is a variable exponent.